Okay, so we will spend the day reviewing how graphs work. And I'm sure that many of you, this will be like pretty easy stuff. Hopefully. Okay, so a well-designed graph is more than a picture worth 1,000 words. It can give you more information than either words, columns of numbers, or equations. To be useful, however, the graph must be drawn properly. We're going to develop the use of graphs to display data. So one of the most important skills to learn driving a car is how to stop it safely. Hands up if you took driver's ed. Just about everyone. Or not, maybe. Okay, so anyways, you all know about the brakes, right? No car can stop on a dime. The faster the car is going, the farther it travels before it stops. Duh. And you took this in grade 10 science as well. If you studied for a driver's license, you probably found a table in the manual showing how far a car moves beyond the point at which the driver makes a decision to stop. Now, most people know that the faster you're going, the longer it takes. But did you know that it's not a linear relationship? I don't know if they teach that in driver's ed. Maybe they don't. One manual shows that a car travels a certain distance between the time the driver decides to stop the car and the time the brakes are applied. This is called the reaction distance. And I know that this is taught in grade 10 science because I teach in grade 10 science. The reaction distance. If you had to define reaction distance, that would be what? It's a distance. It's the distance that the car goes when your brain registers you have to stop and your foot actually gets to the brake pedal. Right? Is it going to be a short distance? Likely. Hopefully. When the brakes are applied, the car slows down and travels the braking distance. So there's two distances. There's the reaction distance and there's the braking distance. Now there's one major difference between those two. The reaction distance, if you're driving on the highway at 100, how fast are you going as you travel that reaction distance? How fast are you going as you travel the reaction distance? Anyone? 100. You're still going at 100. Your foot has not hit the brake yet, has it? You're still going 100. You're going pretty fast. Hopefully that's a short enough time, though, right? Table 1 of the bar graph, figure 1, show these distances together with the total stopping distance for various speeds. So, if you're going 10 meters per second, with a certain reaction time, you'd travel 7.4 meters before your foot hits the brake. You would travel, their braking distance would be 9.1 for a total, add them together, right, of 16.5. And so on. If you're traveling 15 meters per second, it's going to take you 11.1 meters to get to your foot to the brake. Did the reaction time change?
Yep.
The reaction time. Does your reaction time depend on how fast you're going? No, the reaction time didn't change. How come the reaction distance changed? Because you're going faster. And the faster you go, it takes 22 meters to get your foot to the brake traveling at 30. Did your reaction time change? No. Does the braking distance change? Yeah, because you're going faster, it takes longer to get to a stop. If you're traveling at 30 meters per second, well, that's a total distance of 104 meters, about the length of the track. No. Pardon me? I'm glad you asked that. How fast is 30 meters per second? We're going to use the magic number. Remember that, Graham, from grade 10 science? The magic number is 3.6. So how do you convert meters per second to kilometers per hour? You multiply by 3.6. Go ahead and do that. Teaching that I'd have those numbers memorized, but I don't. Well, the first one's easy, right? 36. 15 is what, about 42 or so?
54.
Is it really? Okay. 54?
72. 90. 108.
108. Okay. So if you're driving 36, you're driving down maybe a small residential street. There's cars on both sides. You're wisely traveling a little bit slower. Hint, hint. You still need 16 meters to stop. How far is 16 meters? Is that 16 meters to the wall? 1, 2, 3, 4, 5. That's not 16 meters. 7, 8, 9. That's only like, what, maybe 10, maybe 12. Farther than that. And then you're only going 36. If you're doing 108, Mike's speedometer doesn't even go that high in my car. 108. You need 104 meters to stop. That's a long way. If you're traveling down the highway at 108, 30 meters per second, if you all you do is, maybe adjust the stereo, maybe your eyes are down for even maybe a second and a half, how far do you go? 1.5 seconds you're going to go? 45 meters. I dare you to walk down the hall with your eyes closed for 45 meters at 108 kilometers an hour. Not going to happen, but people do it on the highway all the time. Anyways, I got to make that smaller. It's too big. The first step in analyzing data is to look at them carefully. Oh, by the way, that is something that you need to know. That is the first thing you should put on your cheat sheet. How many people think it might not be a terrible idea to have like a cheat sheet on the go kind of thing? Big discard. Would it be more than one sheet, you think, Graham? Like, would you need like front and back? Probably, but then you can have it and then take it and condense it down. Oh yeah, I don't need to know that. Right? If you want, that's not a terrible idea to have a cheat sheet on the go kind of thing. I guarantee you the 3.6 you're going to need. Now, remember, if you're going from meters per second, 2 kilometers per hour, it's multiplied. And if you're going from kilometers per hour to meters per second, it's going to be divide. You need to have that on your cheat sheet. I'm not going to give that to you. Okay, so we're analyzing data. Which variable did the experiment or the driver change? In our example, it was the speed of the car. Thus, speed is the independent variable. Have you heard that term before? You probably have. And again, this is all graph review. I just want to make sure that everyone's got these skills so we can move forward. Independent variable or the manipulated variable. Now, the other two variables, reaction distance and braking distance, changed as a result of the change in the speed. These quantities are called the dependent variables. Where does the independent variable go traditionally on a graph? On the bottom, that's your x. The dependent variable traditionally goes on the y, okay? There are times when we manipulate that for our own purposes, and I'll explain that as that situation arises. But generally, I'm not a big fan of the word always, because always means always with no exceptions. So I will usually say generally. Generally, the independent variable goes on the x, and the dependent variable goes on the y. How do the distances change for a given change in the speed? Notice that the reaction distance increases by about the same amount for each increase in speed. Look at these numbers here. Should these numbers go up by the same amount? They sort of do, right? Like 7.5 to 11 is like about, 3.5 or so? They're going up by about 3.5. They should. How come? These are going up by 5 every time. What type of relationship is this? Is it going to be a straight line relationship or is it going to be a curvy relationship? Straight line. And that makes sense because you're traveling at a constant speed, and I asked you, does the reaction time change? And you all told me no. The reaction time doesn't change, it's only the speed that changes. So how do the distances change? It should be a linear thing, right? And is it? It's this one right here. Is it linear? Look at that, it's a perfect straight line. Is it easier to see from the graph or is it easier to see from the data? Most people would say from the graph. Very few people can look at those numbers and say, oh yeah, that's linear. I certainly can. The relationship between the the braking distance, however, increases much more as the speed increases. Look at this. As you go up from 10 to 15, it went from 9.1 to 20. About 11. Here, we went another 5, it went up by 16. Are these going up by the same amount each time? No. This graph we can see is going to be linear, and this graph we can see is going to be curvy of some nature. The relationship between the distances and the speed can be more easily seen if the data are plotted on a graph. To avoid confusion, you should plot two graphs, one of reaction distance and the other braking distance. And I did that for you down here. So this one here, the line is the reaction distance. This curvy one here is the braking distance. And what's the yellow one? It's not yellow on your page, obviously. That's the total. It's what you get when you add that plus that, you get that. And it should be no surprise that that is also curved. Okay? Okay. How do you plot graphs? Again, you guys know all this stuff. Just review, make sure everyone's on the same page. These steps will help you plot graphs and data tables, which you're going to do hopefully this period. Identify the dependent variables. Again, independence on the x, dependence on the y. Determine the range. Here's one that I always have trouble with students. They always say, what should it go up by? You guys have to be able to start doing that on your own. Okay, determine the range of the independent variable. In the example, the data are given for speeds between 10 and 30. Go back to the data. We start at 10, we go to 30. Should I just go from 10 to 30? Why, Nick's shaking her head. Why not? Should I include 0? You can. Is it a good idea to include 0 if you can? Yes, it usually is. If 0 is within the sort of ballpark, try to include 0. And that's what they're talking about in number 3 here. Decide if the origin is a valid data point. When the speed is 0, reaction and stopping distances are obviously both 0. If you're traveling 0 meters per second, your braking distance is 0. You're stopped. Should you include 0, 0 if you can in your graph? Yes, you should. Spread out the data as much as possible. I see this all the time. People stretch their data, their graph into a little tiny like thumbnail size when they've got a huge page. Should you do that? No, you can't see the trends. Okay? Make it as big as possible. Spread out the data as much as possible. Let each space stand for a convenient unit like 2, 5, or 10. Should you number and label the horizontal axis? Yes, you should identify it, what it is. You should label it. It's the speed. Repeat steps 2 to 4 for the dependent variable. Plot your data points. Here's a big one. Draw the best straight line or smooth curve that passes through as many data points as possible. Do not use a series of straight line segments that connect the dots. Do not connect the dots. It is not a children's connect the dot exercise. Do not connect the dots. You want to come up with what's called the line of best fit or the curve of best fit. Have you heard that term in math before? Line of best fit? Curve of best fit? No? Okay. In the old applied math program, we dealt with that quite a bit. I'm going to show you a line of best fit right now. This is going to be exciting. As you know, I'm a bit of a nerd. I want to show you what I did here. I took my grade 11 marks and my grade 11 absences, and I created a graph. And in a spreadsheet, it's pretty easy to do. You just type them in. Where's the graph here? Working. There it is. Oops. Absences across the bottom. I need to make this a bit smaller. Okay, awesome. Absences across the bottom, mark across the top. So, this student here had 7 absences. Their mark was about a 60 or so. I added in a trend line, a line of best fit. Did I connect the dots? I would get some squiggly thing that would mean nothing. I added in what we call a trend line, and what would you say the relationship is between attendance and marks? Less attendance, less marks. Is it a linear relationship? Is it direct? It only makes sense. If you were only in class one day, what would your mark be? Lousy. 0. Now, is it a strong relationship? Well, the data is pretty scattered, isn't it? Like, it's all over the place, right? Like, look at this person here, we'll say, had 14 absences. Highest mark in the class. Now, what were those 14 absences for? Who knows? I don't know. I don't even know who that is. Could be school-related kind of things, right? This person could be one of those sort of, high-achieving kind of, they stay caught up. This person way out here with the most absences, they had about a 64, 65. I would think with that number of absences, they did pretty well. This number right here, this R squared number, 0.075, that tells me, because I know some stats, tells me how good of a fit it is. Is that a real linear relationship? Like, is it really all the dots in a line? No, not even close. If it was really good, it'd be a -1, R squared. Okay? Now, this is only one class. If I took the entire school, what would you imagine it would look like? Would you see more of a line? Probably. If you look at those data points right there, and everything else is sort of like, on either side, you can sort of see the line. I see it there. I'm going to show you the grade 12 one as well. Is it going to show me the graph? Is that more of a statistical relationship, do you think? Look at those, eh? You got almost 40, Adams has got a 60. Good question. Do you see more of the trend here? Absolutely, I see it. That's only 2 classes. If I took all grade 12s, what would you see? You would see more and more data points that would be closer to that line and less of these outliers. Obviously, attendance matters. Just want to point that out. Okay. Give the graph a title that clearly tells what the graph is. I would have lost a mark here because I didn't do this. Grade 11. This is grade 12, thank you. Grade 12, marks. Did I spell it right? Yes. Now, this brings up why didn't it do it? Okay. Did I not press enter? Press enter to apply. Yay. When it says marks versus attendance, the first thing is the Y versus the second thing, which is the X. Okay, so it's always Y versus X. All right, back to this here. I can tell you guys I'm losing you. We got to get doing something here. Okay, linear relationship. There's linear, quadratic, and inverse. This is linear because it's a straight line. What's the general formula for a straight line? Y equals mx plus b, where m is the slope. Do you remember how to calculate slope? Rise over run, very good, right? Rise over run, it's right here. So in this particular case, I picked 2 data points. I'm using these data points right here. I'm using that one and that one. So the y value here is 18.5. Remember this? y2 minus y1 all over x2 minus x1. Has anyone never seen that before? Good. You can all calculate slope, right? We're going to find out. So it's 18.5 minus 7.4. The x here is 25. The x here is 10. Does the y have to be on top? Yes. The x have to be on the bottom. So I get 0.74. And what's the little letter right there? Seconds. Why is it seconds, Nick? What is that 0.74 seconds in this particular example? It's that thing that doesn't change that I asked you about before. Reaction time. This person had a reaction time of 0.74 seconds. Where did I get the seconds unit from? What is the unit for distance? The unit for the y here is, need a little more space. The unit for the y is meters, and the unit for x is meters per second. Now, remember learning fractions in about grade 8 or so? How much fun that was? Not so much. How do you divide fractions? Do you remember? Very good. So it's meters divided by meters per second. Can you do this with units? Like, is this okay? Yeah. Mr. Friesen used to call this dimensional analysis. Big fancy word for manipulating the units. Meters. What do we do, Monique? Change this to multiply. Flip the second one, right? And now I got meters times seconds divided by meters, and what happens? The meters cancel out, and you get a unit of seconds. Will the slope always have a unit? Yes. Because the slope has meaning. In math, it's just some arbitrary number that nobody cares about. In science, we care about it. What does it mean? I will expect you to know what the slope means. One way to figure it out is to figure out what the units are for it. It's going to be the y unit divided by the x unit. Seconds. 0.74 seconds. It is the reaction time. That's what they're talking about on that next page there, right there. Okay? If the slope is a property of the system, the slope always has a meaning. Linear relationships are never always straight up. We saw that with the marks. It can have a negative slope. In fact, if I go back to here, I don't actually know what this equation is, do I? It would be nice if it told me what that equation is. That if I knew what the equation was, I could predict your mark based on your attendances. I don't. It's too bad. Okay. This is a quadratic relationship. What's a quadratic equation? Jake, do you remember from math class, quadratic? No? Anyone else? Quadratic? Cole? Math? No? Matt? Remember? well, that's the next step, I suppose. Quadratic relationship is one with a, x squared. Quadratic is squared. A cubed one would be a cubic, right? Cubic, yeah. We're only going to deal with quadratic ones. Okay, the graph figure 4 braking distance versus speed is not a straight line, but rather looks like a parabola. You probably heard that word too, Matt, right? Parabola, x squared. Remember probably doing this stuff? That was fun, right? Finding the zeros and all that. Bunch of junk. This indicates the braking distance varies as the square of the original speed. In other words, if you double your speed, the braking distance increases 4 times. How come it's 4 times? Because it's 2 squared. The graph's slope changes, so it cannot be calculated. Can you find the slope of a curvy line? No, because it changes. You can, however, calculate the slope of a curve at an instant by drawing a tangent line. More on that in a bit. Here's a question. I'm almost done, I promise. If it takes a person 40 meters to stop after driving 50 kilometers an hour, how far will it take to stop if driving 100? Is it 80? 160 is the correct answer. Who came up with that back here? Way to go. How'd you come up with 160?
40 times 40 squared?
40 times 4. Yeah, right. That's kind of hard to describe, right? Yeah. You knew what you were doing, you just didn't know how to describe. The speed was 2 times, right? Right? Will? Right? Two times the speed, so 50, 100, right? 2 times the speed. So this is what he did. Distance is 2 times squared, which is going to be times by 4, and it was 40. Well done, 160 meters. Twice as fast, 4 times as far. That's a good thing to know. They should teach you that in driver's ed. Has to do with kinetic energy. You'll learn about that in grade 12. Okay, blah, 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 blah. We're done, Mr. Bennett. Stop talking, right, Nick? Yeah. Some relationships are such that one quantity increases, the other one decreases. This is called an inverse relationship. Its graph would look like figure 5. Again, you may only want to determine the instantaneous slope by applying the tangent line. You should know the 3 types of relationships: linear, quadratic, inverse. Know what the graphs look like. It's on the board. Okay, I'm done yakking. You've got 20 minutes. Here's a bit of a review. They're not easy questions. Generally what happens is I'd say I can give you 20 minutes, and after 5 minutes I realize that I have to actually work through them with you. Take 5 minutes and try it. How about we treat each question as one, and then I'll give you a little time. Suppose a student during a lab determines that the y-intercept for a graph of reaction distance versus speed was 3.4. Y-intercept. I never really talked about that, did I? What is the y-intercept? It's where the what? You said it right.
Point where the graph crosses the line.
Exactly. So, like, if I were to draw this graph, it would be that point right there, right? Okay, and this is reaction distance versus speed. So speed is down here. And this is reaction distance. What would this mean in real life? That would mean that if the speed was 0, the reaction distance was, in other words, I'm driving down the road at 0 meters per second and I require 3.4 meters to stop. Does that make any sense?
You're teleporting.
Apparently. I still need a stopping distance even though I'm going 0. Is it possible? No. This is an impossible situation. Draw a sketch of what it would look like. It would look like that. Draw the graph.
Even if we were teleporting, it's not possible.
Exactly. And my flux capacitor is running a little low. Not possible. Now that I've explained it, does it make sense, Graham? Yeah. Number 2 is actually easier. In the earlier braking example, at what speed is the reaction distance 10? At what speed is the reaction distance 10? We're talking about, what line are we talking about? We're talking about this one. Reaction distance. At what speed is the reaction distance 10? 10, right there. What speed?
Like 14.
About 14, maybe 13 and a half, somewhere in there. So my answer was, we're going to say about 13 and a half. Would you agree with me? Could you have done that if I'd shown you the graph right away? Shown you the graph, could you pick that out? I'm hoping you could. Everyone in the room should be able to do that. Okay. Here's a harder one. A graph of reaction distance versus speed, and the slope is found to be 0.74. That's the same as this one right here, right? Wasn't the slope 7.4? Okay, awesome. The letter M is for slope, right? Okay. Now it says, suppose another experiment is made and the slope is found to be steeper. What does this mean?
The reaction time is slower.
Slower or faster?
Look at the bottom for stuff because it's going farther.
Is he right? Come on, Wayne, think about it. If it's steeper, would it be the blue line? Obviously, right? Steeper is that, which means the slope is bigger or smaller? Bigger, so give me a number that's bigger than 0.74. Well, 0.75 is not that much. How about 0.9? Would that be okay? Okay, so 0.9, which means his reaction time is longer, which means he's slower. You're absolutely right. He's texting or doing something, he or she. What does it mean? It means that they have a slower reaction time. Okay, last one. Figure 6 shows, that's this one right here, shows the relationship between the circumference and the diameter of a circle. Circumference and diameter. Would a different circle circumference create a different graph? If I graphed a different circle, would I get a different graph? Just because I'm not saying anything isn't an indication of your answers being correct or not. I am merely waiting for people to think. Would you get a different graph if you get a different circle? Hands up if you think it's a different graph. Be brave. Graham's the leader. Awesome. Who thinks it would be the same graph? Who doesn't know? You can't do that. I have a question for you. How many circles are represented in this graph? Just one? Even more than 15. I show circles that have 1, 2, 3, 4, and 5 centimeter diameters, as well as 1.5 and 2.5 and 3.5 and 4.5 and 1.25 and 2.25, and like basically an infinite number of circles from ranging from 1 to 5. So would a different circle have a different graph? No. In fact, it would be exactly on that line. It'd be a perfect linear relationship. It would be unlike the Marx one. Why would it be perfect linear? Well, because it's a perfect circle. What is the meaning of the slope? What is the meaning? I should really ask part C first. What are the units of slope here? Let's do part C. What's the unit for the y? Centimeters. What's the unit for the x? Uh-oh. So what's the unit for the slope? Nothing's. It doesn't have a unit. That doesn't help us. Let's look at the quantities. What is the quantity on the x? It is circumference. What is the quantity on the, sorry, I said x, didn't I? Circumference on the y, diameter on the x. What is c over d equal to? Anyone know? Anyone remember the circumference of a circle formula? Pi times d, write your R-gram. Divide both sides by d. You get c over d equals our old Egyptian friend pi. It was the Egyptians that first discovered it. What is the slope of this line? Pi, 3.1415926. I haven't got it memorized past that, sorry. It's the slope of that line. It is the value of pi. How come it has no units? Does pi have units? It's just a number. What is pi? It's the ratio of the circumference to the diameter of a circle. I've thrown a lot of stuff at you, haven't I?
Yeah.
I've basically taken almost everything you've learned in math in the last 8 years and thrown it to you in about 20 minutes. Fear not, my friends. I will be with you on this path. Do not worry. Okay. I'll start you with an easy one. You've got 9 minutes left. If you can't do question number 1 in 9 minutes, then you'll have to do it at home. Do number 1. All you have to do is read the graph. Can you read a graph? Do number 1 for tomorrow. We'll check it first thing. And then I'm going to give you time to do 2 and 3. Go.